So we know where the Earth came from, the solid Earth, and we know roughly where its initial atmosphere came from. And now we want to turn our attention to looking at climate and climate variations at various times during the Earth's existence. And the first thing we want to do is have a quick look at a timeline for the planet. So I have here a link. As you can see, it's from New Zealand. This is what the link looks like, and I have no idea what all this stuff at the top of the page is about, but it's this stuff down here that I want you to pay attention to. So I want you to visit this link and take a look and basically look at everything. The first column is the name of the period. Some of these names are familiar to some of you, hopefully at least some of them. For example, the word Paleozoic. It's one of those things that goes around, Precambrian, and so on and so forth. At the top of the table is the current time, and it goes all the way down to the beginning. The hot universe, matter, radiation, soup, formation of the universe, and then I guess the planet appears somewhere in there. We're not going to pay so much attention anymore to that early stuff. Then in the second column are names that may also be familiar to you. These are geological names to refer to eras. So we're currently in what's called the Holocene, and prior to that was the Pleistocene, and so on and so forth. If you go down, you'll see all those. The third column and the fourth columns are particularly important. They describe the climate and some other things. So for example, let's look at the current climate, AD 1350 to 1800, the Little Ice Age. We're going to look at that in a few minutes as part of this clip. Let's go down to the Jurassic, for example. The Jurassic period, mild climate, continents low with large areas covered by seas, mountains rising from Alaska to Mexico. The zenith of dinosaurs, flying reptiles, blah blah blah. So there's some stuff in here about what kind of animal life was on the planet and what kind of plant life was on the planet. And then the final column over here on the right, I do want you to pay attention to that. This looks at what the arrangements of the continents was at the time in question. So if we go back up to the top, we see something more familiar. This yellow thing is South America, the pink thing is Africa, and if you go back in time, you see that those two were once attached to one another. And then even further back in time, that whole blob existed over what we would now call the South Pole. Going back up to the top, light blue is North America, green is Europe, Eurasia. So pay attention to these. In this most recent one, you can see India right here. India is a little triangle of land that has floated up across the Indian Ocean and attached itself. So you can see in the Paleocene down here that India is way down here off the eastern coast of South Africa, making its way northward. And it's that collision, incidentally, that's created the Himalayas. So I want you to be familiar with this timeline. I want you to look at it. The earliest times are at the bottom. Read the text in the main column and study the land masses in the right column. And the reason why, of course, is that if you happen to grow up to be a person who's really interested in, let's say, the Cretaceous period and wondering what the climate was like at the time, then you have to also know what the land masses were like at the time, because this has an influence on ocean flow. For example, as you can see down here in the Jurassic, there's really no gap between Africa and South America. But as that begins to open up, then you can get ocean flow developing through that region, and that could radically disrupt the flow of water around our planet. Now, when we're thinking back over past climate, something we have to be aware of is the so-called faint young sun paradox, or the faint early sun paradox. And this is how that works. Astronomers who study the evolution of stars from beginning to end believe, based on their work, that stars become more luminous the older they get until they finally blow up. And according to the standard model of solar evolution, then, our sun is currently about 30% more luminous than it was billions of years ago. In other words, if you'd been standing on Earth billions of years ago, although you would have been able to see our sun, it would have been 30% less luminous, fainter, and therefore there would have been less solar heat coming in to heat up the atmosphere. So this alone should tell us that the planet was much colder and the atmosphere was much colder. And as a matter of fact, it might have been, according to the solar model, cold enough for water to freeze out. So you couldn't have any liquid water components. So the atmosphere would have been below freezing. On the other hand, all the geological evidence, or at least most of the geological evidence, suggests that the opposite was true, that in fact for most of the history of our atmosphere it's been warmer than it is today. And that's why we call this the faint young sun paradox. What is the resolution? The resolution is the greenhouse effect. It must have been that there was an atmosphere containing greenhouse gases which kept the atmosphere warm enough when the sun was faint, kept the atmosphere warm enough so that liquid water could exist and an operating hydrologic cycle could be maintained. Couple of other things to be aware of. This is discussed in the book, The Idea of Snowball Earth. This is on page 50 of the book. And we can also have a very quick look at Wikipedia. Snowball Earth is the hypothesis that Earth's surface became entirely or nearly entirely frozen at some point in time, at least 650 million years ago. The dinosaurs died out about 65 million years ago, so we're talking about 650 million years ago. Proponents of the hypothesis argue that it explains sedimentary deposits. Opponents of the hypothesis, I'll let you read this for yourself. It is by no means a sure thing that Earth ever went through a snowball phase where all of the water froze out, but there is at least a suggestion of it, and so this comes under the heading of something we want you to be aware of. Another thing to be aware of is something called the KT boundary. Let's go back to our timeline here. This is at 65 million years ago. So here we go, 65 million years ago. This is the KT boundary between the Cretaceous period and the Tertiary period. That's what KT stands for, although really obviously it should be CT, but people call it the KT boundary. 65 million years ago, mass extinctions. There's actually something interesting about this. Here's a Wikipedia link that I forgot to open. Let's try opening this and see what happens. Alright then, so we're talking about the KT extinction event, and as the Wikipedia page shows you, this was a mass extinction of some 3/4 of plant and animal species on Earth, including all the dinosaurs except the ones that could fly. This is a pretty big deal. 3/4 of everything living on Earth went extinct. And the current thinking about the cause of this is that a big asteroid came in and collided with Earth. Can that happen? Yes. I've got a couple of other links here. This is a YouTube link. You can see it up here in the URL box. And back in February of 2013, there was a meteorite that came in over the skies of Siberia, and it turns out that a lot of Russians have dash cams in their cars, and so many of those recorded what this looks like, and there was one of the examples. And here comes another, that thing up there. That's a small meteorite coming in. Well, actually, that's probably a somewhat larger meteorite. But what we're talking about is an asteroid, a chunk of rock several kilometers or several miles wide. And here's another YouTube link where somebody made an animation of what a collision between a meteorite and Earth might look like. Let's see, this lasts for 7 minutes, so I mean, here you are, here's the meteorite looming over Earth, and then here's the meteorite colliding, and this is an animation of what would have happened. So you can look at that if you feel in the mood to look at that. Okay, so the idea is an asteroid came in and impacted, and that impact would have had a couple of effects. Okay, here's my fantastic cartoon. We start out with Earth. I didn't mean for Earth to be red, but doesn't do any harm. So this is Earth minding its own business, and in comes an asteroid. And it isn't going to be anywhere near this big, but just so you can see it on the screen, this is what we're talking about. The asteroid has a mass given by little m, and it's traveling towards the Earth at speed v, so it has a lot of energy associated with it in the form of kinetic energy, mass times speed squared over 2. And when this asteroid collides with Earth, all of that kinetic energy has to go somewhere because of the law of conservation of energy. So there's an enormous energetic input at the time of collision. Some of that energy will go into the form of thermal energy. So first of all, you just have the collision itself, and the biggest rocks thrown up will fall out very quickly in the region of the impact, but thousands and thousands and billions and trillions of tiny bits of dust and ash will be thrown up into the atmosphere and quickly carried around the entire planet by the prevailing winds. Also, because of the heat, let's see, what shall we have? Let's have blue for fires, because that's unusual. Because of the heat, remember, in comes all this kinetic energy, and it may turn into thermal energy, at least some of it will. So everything will catch fire, and the catching fire means that there will be a lot of soot and smoke in the air as well. So that adds to the general haze. So not long after the impact, I would say within a matter of weeks, easily, you have a haze covering the entire atmosphere, covering the entire planet. What does that mean? Well, it blocks out sunlight coming in from the sun. Here's sunlight coming in, and it no longer can penetrate down to the surface, so the surface is going to get a lot colder, and that's going to have two effects. First of all, photosynthesis is going to die away, so that's going to be problematic for you. And secondly, if it gets cold enough, which it will eventually, or at least it can, then liquid water is going to freeze out. You won't get any rain, you won't get any rivers flowing. All of the dinosaurs that are walking around won't be able to eat any food because photosynthesis has ended, and because all the lakes are frozen over, the dinosaurs won't be able to get any water, so they're just going to drop down dead. And so later on you've got dinosaur skeleton. I have no idea what a dinosaur skeleton looks like, so we'll give it a couple of legs, a couple of forearms, and some big funky looking dinosaur head. So the thinking is that an asteroid collided with Earth about 65 million years ago and killed off a bunch of species because of atmospheric effects, namely blocking sunlight coming in and maybe freezing out surface waters. And just as a matter of interest, there's a signal of this event worldwide in the existence of a layer of an element called iridium, which is very rare on Earth. However, as this little diagram over here on the Wikipedia page shows, if you dig down far enough anywhere on the planet, you find a layer of rock, here it is in this diagram, which is rich in iridium. Okay, so iridium, very rare on Earth, plentiful in asteroids, and everywhere you look on Earth, if you dig down far enough, which means dig down back in time, you find a layer of iridium. And that's one of the clues we have to the fact that there was this big collision. Now we're going to focus in on the last million years. That is from the late Mesozoic. So let's go back to our time series. Here's the Mesozoic. The mass extinctions were about 65 million years ago. As you can see, prior to that we had tropical to subtropical climate everywhere, but after the extinction, mild to cool climate everywhere. So there really is a big dividing point here. It was warmer before the KT boundary and cooler after the KT boundary. There are fossils of dinosaurs and of tropical plants found at high northern latitudes, so they could not possibly have been there unless it was warm once. There's evidence that CO2 levels were much higher than they are today, and we also know from these diagrams off to the side of our timeline that land masses were in very different locations than they are today. Then after about 2.5 million years ago, we started moving into a period of glaciation. Let's see, where are we? In the Tertiary, in the Pliocene, cooler climate, continued uplift and mountain building, widespread glaciation in the northern hemisphere. But then as we get into the Pleistocene, climate fluctuating, cold to mild, the era of ice ages. So that's what we're focusing in on now. About 2.5 million years ago, planet-wide glaciation began to occur. So between 2.5 million years ago and now, we've had glacial periods when it's been cold and glaciers have advanced and covered the landmass, and we've had so-called interglacial periods when things have warmed up and the glaciers have retreated. And as you probably know, we are currently in an interglacial period. And there's been some very interesting studies of the connections between temperatures and things like atmospheric CO2 and methane, and this next diagram shows you that. So this is an ice core record taken from an ice core at Vostok in the Antarctic. On the bottom right is the current time, and the bottom left is 45,000 years ago. Okay, so we're not talking about billions of years ago anymore. We're talking about 45,000 years ago. So we're somewhere in here in the Pleistocene. Okay. On the left-hand axis, and this is in blue, is temperature, and the zero temperature line is way up here. Okay, so if you look at the blue line, just the blue line, anything below the zero line is colder than now, and anything above is warmer than now. So starting now, the present, there's a lot of jiggling, but if we go back about, looks like about 15,000–20,000 years, the planet was quite a lot colder than now. 8 degrees Celsius colder than now. Going back further, the planet was warm, further cold, and so on and so forth. So we would see these as the interglacial periods of time, and we would see these as the glacial periods of time when the glaciers are advancing. And one interesting thing I think I could say is that starting in the past and working forward, it looks as though the Earth got slowly colder, and then boom, jumped up to be warm very rapidly. Gradually colder, rapid warming. Gradually colder, rapid warming. Gradually colder, rapid warming. And now, of course, we are in an era where there is probably also rapid warming associated with man-made increases of greenhouse gases. Which brings me to the red line here, which is the amount of CO2 in the atmosphere. And this is from the ice core. Remember that you drill down, you bring out an ice core, and you can very carefully extract air bubbles from when the ice was formed up to 45,000 years ago. And those air bubbles contain ancient air, and you can analyze the ancient air for the amount of CO2. And there's an astonishing correspondence. When temperature is high, CO2 levels are high. When temperature is low, CO2 levels are low. It's just an amazing correlation. And nobody thinks this is an accident. Everybody thinks that this is perfectly reasonable. Lots of CO2 means you have a strong greenhouse effect and the atmosphere should be warmer. The big question, of course, is which comes first. Remember that you have an ice core and you have to use, and we talked about this when we talked about isotopes a couple of clips ago, you have to use independent dating methods like radiocarbon dating methods to figure out the time at which that ancient ice and the ancient CO2 was laid down. So that gives us this axis. And those radiocarbon dating methods are not yet good enough to tell us which comes first. Does the CO2 go up first and then the temperature go up? Or does the temperature go up and then the CO2 go up? So you just have to stay alive for a few more years or a couple more decades until scientists can do a better job of estimating that quantity. So we notice that there's a very strong correlation between temperature and CO2. That leads us to ask which leads which, and we don't really know just yet. At least historically, that doesn't necessarily mean it has to be the same in the future. One more piece of terminology for you. LGM refers to the last glacial maximum, and that was about 20,000 years ago. So we're in about here this time. Remember, this is now going backwards. Roughly 20,000 years ago was the last time that glaciers covered the earth and so forth. So that's called the LGM, the last glacial maximum. Much colder, of course. A lot of the water was locked up into ice, so sea levels were thought to be about 125 meters lower than they are now, and also much lower CO2 concentrations, about 180. According to this chart, CO2 is now at about 280, but take it from me, it's recently gone over 400. So again, if you look at CO2 levels over the last 45,000 years, they don't ever seem to have gone much over 300, but earlier this year, in the year 2012, they tipped over 400 for the first time. All right. So focusing on the climate of just this last million years, we find that these variations in temperature are to a considerable extent explained by orbital variations and orbital characteristics of Earth. So now we want to spend a few minutes talking about orbits.